All right, I'm going to go ahead and get started. Main thing I'm going to talk about today is kind of the rules of engagement for the final project. I know I'm acutely aware of the fact that we're halfway through the semester, at least in terms of lectures, but my experience in teaching this in the past is that it's better for people to start looking at this earlier than not. But before I do that, I want to close off one thing that I didn't talk about last time because I couldn't find my slides for it, which was particle-particle-particle mesh methods for molecular dynamics. So, because there's a number of interesting aspects to it, and it's a very widely used method. So, molecular dynamics, we want to simulate a collection of n physical particles evolving under Newton's laws for classical mechanics. So you have, each particle has a position, a velocity, a mass, and it evolves under, the Newton's law. So, and the force is given by the gradient of a pair potential. So, as in this case, when we want to do n-body calculations for Coulomb or Newtonian forces, inverse square laws, you have a collection of particles with charges or masses, each of which induces a contribution to the forces, to the force function at any point in space via Coulomb potential. So so the force induced by a single particle is the gradient of the Newtonian potential, and then the force from all the particles is the sum over the forces. So computing forces on n particles is an order n squared calculation because each force on each particle requires order n operations, and then you have n particles. You can't use pick. As I said last time, short range nature of the forces keeps that from being appropriate for particles. For PDEs, for Lagrangian discretizations, it's fine. So here's what you do. You split things into short range and long range. To compute a force on a particle, the red particle, say, you represent it as a combination of contributions from forces on the black particles, which are nearby, using local n-body calculations, and forces from faraway particles using pick, and those are the blue particles. So how do you do this without double counting or having many pick solves? Another question is, does this have a sensible way of thinking about the error? What are the and one of the things that I've been kind of emphasizing over and over again in doing these lectures is error analysis, is that there's actually mathematically systematic ways of estimating error. This is not just because that's my training, but it's also because one of the things that you want to think about is when you have algorithms outside of something that's very simple, you are constantly trying to trade off which things are going to cost more versus giving you more accuracy, and different mechanisms for getting more accuracy. So you'll see an example of it in P cubed M here. So the other thing that makes it hard or interesting is that this isn't, these particles are not Lagrangian markers for an underlying PDE solution. It is an arbitrary distribution of a finite number of particles. So you can't use you use any possible fact that the particles are smoothly distributed or anything else. So here is particle-particle-particle mesh due to Hockney and Eastwood. You express the potential as a sum, a particle-particle contribution and a particle mesh contribution. The particle-particle contribution has localized support outside of absolute z greater than delta, or outside of radius delta. The particle-particle forces are 0, and inside of delta prime, where delta prime is comparable to delta, it's the entire potential. So this is the singular part of the Coulomb/Newtonian potential. And but you've localized it. Outside of some finite support, it's 0. And GPM is whatever's left. So typically the way you get GPP is to multiply your original Newtonian potential by some modifier with compact support, some function with compact support that's identically equal to 1 on this in this uniform region. Those are easy to construct on the delta prime region, delta prime ball, and go to 0 outside of delta. And then GPM is whatever's left. So what you're going to do is you're going to compute the particle-particle contribution to the forces using an n-body calculation. And then we'll compute the particle mesh part of the forces using PIC. So the cost of the particle-particle part of the calculation is, as we discussed last time, order the number of particles squared times the size of the correction region cubed. So you cut down the amount of n squared work you do by the size of the by delta cube, the volume of the of these regions. Now, the course of the particle mesh calculation you're going to see is it's going to look like PIC. So it's going to be order of the number of particles plus order of n log n, where ng is the number of grid points. So there are issues of how do you implement, and I'm going to defer that one till we talk about this again, and then what is the error, and that's the one I want to talk about in a little more detail. So I'm going to talk about how do you implement PIC when we actually do it in homework, and then what is the error. Here's what it looks like. So what's the error in the particle mesh force calculation? First of all, how do you do the particle mesh force calculation? So what you do is you say, I'm going to compute the charge / mass on a regular grid. So it's going to be this is the q sub k, which is the charge of your particle, times some function which is capital phi of I times hg. So these are evaluated at grid points. So think of this as a kind of approximate delta function, if you like, on your hg grid. So you have one for each particle centered at the location of the particle. Second step is that you now have charges on a grid. We can actually compute exactly, because GPM is no longer singular, we can actually compute exactly the convolution on a grid of those charges with the particle mesh part of the Green's function. It's an exact calculation. That's what you have here. And then you compute forces on the grid by taking finite difference gradients, for example, and then you interpolate those forces back to the particles using the same psi function that you used to deposit the charges in the first place. So that's your typical particle mesh force calculation. I want to focus on the first two steps to understand what we're doing here. I mean, the question really is, this is an algorithm, it's completely well defined, but why should it work? We don't have any real control over the locations of the particles. They're in no way smoothly located or located on a rectangular grid. Nonetheless, this does work. So here's the way to think about what the approximation we're making. So GPM is smooth, therefore the field induced by it is smooth, in principle at least. And therefore, the error in doing either finite differences or to compute forces or depositing those forces onto the grid, I claim is if we can resolve, is going to be an application of the first set of ideas that I talk about. So what I'm going to talk about is, let's just look at the act of computing the field on a grid. What is the error that we commit by going through this process to compute the field at grid points, as opposed to computing it directly using the n-body calculation? So to compute a field at any point, qk gpm of x minus xk, sum over k, we're approximating that by gpm of x. Well, x here is a grid point, but you can ignore that. Time minus GHG times rho GI. So we're approximating this convolution with a sum over grid points. Now we, so I missed looks like I missed a sum here. There should be another sum over k. So ignore the middle line, look at the bottom line. When I put in the definition for this, which is a sum over k, which is this thing up here, what I get at the bottom is sum over k, q sub k, sum over j, gpm x minus j times hg times psi of j minus hg, of j of hg minus xk. So the point is that in depositing the charge, the way to look at it is that the way we are approximating, it induces an approximation to the particle mesh part of the Green's function, that gpm of x minus xk is the sum over mesh points of gpm of x minus jhg times psi of jhg minus xk. So this is the thing that is meant to approximate this. Does it approximate it? But this is all just following the definitions around and see what you get. So in what sense does this guy here approximate this guy here? Well, typically so GPM has, it's a continuous function where we can estimate the derivatives. So we go ahead and perform Taylor expansions and see what we get. So we take a Taylor expansion of GPM of x minus y about y equal xk. And when we do that, we get GPM of x minus j hg, psi of jhk minus xj. So I'm taking a Taylor expansion of this here, of g, and that's g of x minus xk times the sum over j of this quantity plus so what I've done is I've taken the Taylor expansion of g, and I've written out the various terms and I've grouped them. So the first term in the Taylor expansion is the sum over j of psi of j times hg minus xk. So that's the sum over grid points of jhg minus xk. So it's a sum of psi over shifted lattice points. Down here, we get the other terms in the Taylor expansion, the next capital P terms. So this is sum over j of jhg minus xk to the p, psi of jhg minus xk. And then we get a remainder term. If I only took this sum up to capital P terms, here's the remainder term. And here I've used the fact that g is a smoothed out version of the Green's function. So what happens is that this looks like something that looks like 1 over x to the p plus 1, if you take p derivatives of it. And then, except that it's been cut off, the effect of introducing the smooth cutoff at radii less than delta prime comparable to delta is that it's no more singular than delta to the p plus 1. So this is as bad as it can get. So all I've done here is take Taylor expansion of this. Now what does that tell us? Well, the first thing it tells us is that if we ignored all the other terms in the Taylor expansion, this would be the leading order term in our approximation. What that's telling us is that this sum of psi of jhg minus xk, so the sum over lattice points of the shifted deposition function, has to be identically equal to 1. So otherwise you don't get conservation of charge. What happens to the next set of terms? So for all, if I go out some finite, for P out to some finite capital P, saying that these guys vanish, those are what is known in this domain as moment conditions. So this is a condition on what happens to sums over lattice points of shifted versions of psi. The 0th moment is identically equal to 1. These powers are identically equal to of the moment. These moments of powers, which are non-zero powers, are identically equal to 0. Now, this sounds like kind of an odd and unnatural set of conditions, but in fact, it's fairly easy to construct psis that meet these conditions. I'll show you at least pictures of examples in a little bit. And there's a natural construction in Fourier space, and there's a natural construction in physical space. And then finally, this is just the remainder term in the Taylor expansion. So let's look at what the error is. So the error induced in the field induced by a single particle. So yes, so this is if this sums to 1, this is just GPM of x minus xk. These guys all vanish. This is the error term. So the error is really just this guy. So the error induced in the field by a single particle is order h to the capital P, and the max of x minus xk delta to the p plus 1. So what happens if we have more than one particle, some nearby, some farther away? And in fact, we're going to assume that we have particles that are at least at some macroscopic level uniformly distributed. So that says that within some sphere of radius capital R times delta, that the particles are on average distributed uniformly with a density q bar. So if we do that, so here's first of all, the error is the sum over all the particles of this guy, qk times hpg times that. What's that equal to? Well, if we have a uniform distribution, then the way we organize ourselves to understand what's going on in this uniform distribution is that we break the space around the space centered at xk into spherical shells of radius r, r plus 1, inner radius r, outer radius r plus 1. And again, we assume that the particles, at least on that, at that level of granularity, are uniformly distributed with a uniform distribution of q bar. So how many such, what's the charge density, what does this guy become in each of those shells? Well, it's h to the p divided by r delta to the p plus 1 times q bar times the volume of that spherical shell, which is r delta squared. So now we go down to here and we do a little bit of algebra, and at the end we get h to the p sub g divided by delta to the p minus 2, and then a sum from r equal 1 to capital R of 1 over r to the p minus 1. Well, so you get an error estimate that depends on p, the order of accuracy, but in kind of a funny way. First of all, if p is equal to 2, then I don't get a uniform bound on this. It looks like log r, and that means I have to go back and do my analysis a little differently, because then I have to say, well, what's q bar really as r gets large? But if p is greater than 2, I get an interesting thing which tells you something about the trade-offs you can make. It looks like order of h squared of the, where hg squared, times hg over delta to the p minus 2. So hg squared says, okay, if I make the grid finer, I improve the accuracy of my particle mesh calculation. This guy here, hg over delta to the p minus 2, that has some, if typically what you're going to do is target delta to be comparable to Hg, some multiple of Hg. So how do I choose that multiple? Well, there are a couple of things that go into this. One is it depends on P. If P is equal to 3, then this guy here has a kind of 1 over that multiple of, has Hg over delta kind of appearing as a factor, so you can get some mileage out of that to make the error smaller. But let's assume, for example, if P were equal to 6. Well, as P gets larger, you get a much larger lever arm in terms of controlling the error in your particle mesh calculation. It's not unlimited, though. Remember, delta is the region, essentially the size of the region that you're doing n body. So as you increase delta, you are going to make the n body part of the calculation much more expensive. But within limits, that may be a good trade-off, because one of the things that you find out when you get into this is that it's much easier to make n-body calculations use cache-based systems very well. You can organize yourself so that locally, at least, you're doing stride 1 accesses. You can vectorize them. There are lots of things you can do to make n-body, because it's such a simple algorithm, go fast. So within limits, it may be worth trading this for doing less work on the grid. So here's an example of what some of the deposition functions look like. Each of these correspond to p equal 2, 3, 4, 6. The p equal 2 is just piecewise linear, and these are all scaled to be for h equal 1. So this is the only one of them, by the way, that's positivity preserving. And that's actually an easy thing to check, because if you want a moment like this to vanish, where one of the polynomials is quadratic, is just x squared, for example. X squared's positive. When you sum x squared against the only way that you sum x squared against periodic images of the shifted psi and get 0 is that at least one of them is negative. So this is kind of the this is the giveaway that to go to higher order, you need to have some of these deposition functions be negative. Now, because these are just something you're doing to get an inexpensive way of computing the far field, it's not as critical here as it would be, say, for if what you were depositing was a distribution function, where it would matter more. W3 and all of the others have some regions that are negative. Here, W3 has a little negative here, a little negative here. As you go to higher order, W4, you get a function that extends out to here. And then W6, actually, what happens is as you go to higher order, the support of these things gets larger. So there's a cost trade-off in going to higher order in terms of how complicated your deposition function is. So the takeaway from all this is first of all, that there is a sensible error estimation that you can do for p cubed m. Wasn't obvious at the start. And that there are design choices in doing p cubed m for the kinds of, between how you do deposition, what grids you choose, and what cutoffs you're choosing in the splitting of the potential into particle-particle and particle mesh. So there are accuracy considerations there. They're all buried in what happens in your particle mesh calculation, because they're all buried in choice of delta. Remember, the particle-particle thing is assumed to be done exactly. So questions? Yes?
Is the choice of delta related to the physics of the problem?
Well, ultimately, yes. I mean, the choice of delta, you're essentially saying that the primary contributor to the force is the far field effects outside of a radius delta. Primary contributor to the force and the dynamics is local end-body interactions. So it's kind of saying, okay, where does the, if you think of this as gravity, where is the scale on which you're going to have things like particles orbiting each other going to be important to the dynamics, and where is it just kind of the averaged effect of the gravitational potential over all the particles? Where's it just mean field? Yes?
Does this hold in non-Newtonian settings, so like in a relativistic setting?
Oh, I would be very cautious to make generalizations, because this is really, okay, so in what sense, to what extent could you generalize this? So let me answer that question instead. What this really relies on is we're not using anything really special about Newtonian potentials, because however, what it does rely on is being able to write the solution to your problem as a convolution. And that I don't think you can do in the relativistic, and certainly not in a general relativistic setting. But here, we could have had any, let's go back. We could have had any force field that's written as a two-body convolution and applied this. So we could have applied this, for example, to Leonard-Jones, and it would have made perfectly good sense. The trade-offs become different, because in Leonard-Jones, instead of having p plus 1 here, we'd have p plus 6 as the denominator, and then you have to do the error estimates come out differently, and but this in an essential way relies on it being a convolution. Other questions? All right. So the rest of the lecture, I'm going to talk about the logistics and the format for the final project. So let me move on. So final projects are to be done in teams of 2 to 4 people. The final report, the final project, it's not just the report, but everything, all of your work product, is due at 11:59 p.m., 12/15/17. That's the last day of exams. We have a set of intermediate deadlines that define a process and also define the work product for your project. We're not going to grade the intermediate work at the various deadlines, but we'll read it to provide you feedback and guidance. They're still required by the end of the project. Now, I've noticed, at least with some students, a certain lack of comfort with Git. For the final project, you're going to have to get really comfortable with Git, partially because you're going to be working as a group, and that one of the main things you use revision control for is to have multiple people working on a single project, so that's your mechanism for communicating. So the thing you don't want to do is have some other mechanism by which you communicate and then submit everything at the end. Please do not do that. That is not the right way to do it, and you will regret it, because if you may find out that things are not hanging together correctly, and it'll be too late to do anything about them. Git is also a mechanism to communicate with us. So for these intermediate work products, checking them into the project repository will allow us to check them out, read them, and give you feedback. So, in order for this not to be so vague as to be useless, what I'm going to do in this lecture is go through in detail the process and deadlines in terms of a project that I've used in the past. So first of all, what are these intermediate milestones? The first one, most important one, is figuring out who the teams are. So you have to self-organize. This is not something we do for you, it's something you have to do for yourself. That's one of the useful things of Piazza, is that you can try to find teams, organize yourselves into teams. And in the process, you're going to have a topic for the project. Once you have that topic, part of having what it means to have that topic is that you'll have a mathematical description of the problem being solved. It can be in the form of a research article combined with a concise summary. All of this needs to be done by the end of October. So it's a low bar. The primary thing that needs to be done is you have to have the team in place. And in order to have a team in place, you have to kind of decide on what it is kind of represents your common interests. So, so that's due on these are all Monday due dates. So it's due on Monday, the 30th of October. How exactly you will inform us of that, we'll figure that out. It'll probably be by something, essentially via email. However, once you have told us who the teams are and what your project name is, we'll set up Git repositories for each project and give the members of the team read and write access to those repositories. So that's going to be your workspace for the project, including the place where you submit the final results. So what's the next intermediate milestone? A complete mathematical specification of the discretization methods or numerical algorithms used to solve the problem. A specification of what will constitute a computational solution to your problem. So this is telling us what it is you want to do, and at least a high level. So at the level of equations still. And that's due the 2 weeks after the projects are defined, 13th of November. And then the third intermediate milestone is a top-level design of the software used to solve this problem. You're going to be writing code, so you're going to tell us what your code's going to look like. You need to tell yourself what your code's going to look like. So the way you tell us that is the way we've been telling you what your code's going to look like for your homeworks. Is you give us header files for the major classes, and in addition to that, a mapping of those classes to the algorithm specification given in the previous milestone. And then a third thing that you need is specification of a testing process for each class. I'll go into a little more detail later on that. That's due the Monday after Thanksgiving, the 27th. So what are these? These are kind of these are kind of mushy sorts of or at least of milestones. At least they admit to multiple interpretations. So what I'm going to do is walk you through, for the case of a project I've used when I've had a large number of undergraduates in the course. And we had a separate undergraduate project. This was an undergraduate project that was curated and supervised by me, done with undergraduates. So it actually was submitted to this same process. So what I'll do is, for that project, I'll give you first the mathematical specification, the algorithmic specification, and talk about the software specification. And this is going to this will, I hope, give you some conceptual template for how your versions of these things should look. So the problem that we were solving for this project was the incompressible Euler equations. The approach we were taking was from a paper I wrote with John Bell and Harlan Gloss in 1989. And these are the equations we're solving. du dt dt is equal to the divergence of uu, plus the divergence of uu is equal to minus the gradient of the pressure. And then you have the divergence-free constraint below. And in fact, we're only doing this in 2 dimensions, and we're doing it on the unit square for some finite time. The initial conditions on the velocity field is specified, so u of x0 is some known function u0 of x, and we assume periodic boundary conditions. So you have periodic images of translates of this unit box by integers that define the solution everywhere, formally, and that's a way of getting boundary conditions as required. I'll just mention that this is slightly mathematically unfamiliar relative to what you might be used to in ordinary differential equations. It's a combination of evolution equations and constraints, so that's why we have to do something that is that makes it look more familiar. Well, one way of doing it is is the pressure Poisson formulation to eliminate the constraint by differentiating it with respect to time and obtaining an equation for P. So we take the divergence of the Euler equation for the velocity field, and that gives us a Poisson equation in terms of the right-hand side for the pressure. The gradient of P has to be periodic, and therefore P is periodic. Here's a slightly different formulation, which is projection formulation. We use a projection operator to make this manifestly an evolution equation without constraints. So projection operator is defined as the identity minus the gradient, Laplacian inverse, divergence. This all makes perfectly good sense when applied to a velocity field. We take its divergence, we take Laplacian inverse on the domain, and then we apply the gradient field. So I've defined what divergence and gradient are. This is all at the level of PDEs. This is all telling us what the mathematics of the problem we're solving. And what is the properties of P? The projection applied to a gradient is 0. The projection applied to U is the divergence of U is equal to 0. If we apply the projection operator to this equation, we end up with this. Now, projection applied to U and divergence of U is equal to 0 means projection just goes inside. Projection of grad P is equal to 0. So we end up with a perfectly good evolution equation. du dt is equal to P of the advective terms, or plus the P of the advective terms is equal to 0. P is this funny operator that involves solving Poisson's equation, but that's okay. This is now something that we have a perfectly good evolution equation for, plus the initial value constraint divergence of U at time t equals 0 is equal to 0. That is exactly equivalent to the first set of equations that we wrote down. So given that this is our mathematical formulation, what do our discretizations look like? So here's the kind of information I want to be able to see. So first of all, I'm assuming that we're on a power of 2 grid, because I'm going to be using the simple versions of FFTs to do my Poisson solves later. And I'm assuming so-called cell-centered discretizations. U at a mesh point I, where I is some multi-index, approximates the fluid velocity at the center of a mesh box, which is indexed by the index of the lower left corner. And phi, if we have scalars, they're also approximate values at the centers of control volumes. Here's how we approximate the divergence. So if I can get velocities on faces, I can compute the divergence, I can compute the advective terms by taking center differences of those velocities on faces. How do I get velocities on faces? Just arithmetic average from the centers. What about this projection operator? So again, we go back here. This is my PDEs written as a pure evolution equation. I need to evaluate this. I need to evaluate P. Then I can evaluate my right-hand side. So how do I evaluate P? Well, I just follow my nose. I know how to evaluate. I know how to compute a divergence using center differences. I know how to compute gradient using center differences. I know how to solve Poisson's equation using a classical center difference approximation to Laplacian. For those of you who are connoisseurs of this sort of thing, note that the Laplacian that I'm using is not equal to the product of the divergence, discretized gradient. We'll have to take that into account in the way we do the time evolution. So again, what I'm doing here is I'm just stating, here's my PDE. Here's the way I'm going to discretize all the things that appear in the PDE. So I've told you how I discretize advection. I told you how I discretize the projection. Now I have to tell you how I do time discretization. I also have to tell you how I solve Poisson's equation. So we have two solver algorithms we need. One is for solving Poisson's equation on a periodic grid, plus we need a time discretization algorithm. So we'll use an FFT solver for Poisson's equation. You'll hear more about that in when we do the particle lecture. And you'll also hear more about the fourth order Runge-Kutta method for time discretization when we do that. But I'm going to give you a little bit of a flavor of this in the context of the incompressible flow. So we have at this point, by discretizing P in space and discretizing our advection terms in space, a system of ordinary differential equations for the discretized variables. Method of line says, take this as a system of ODEs and just solve it. So the method we'll use is fourth order Runge-Kutta, generalizes Simpson's rule for integrals. So you have to, if you have a right-hand side f, dq dt is equal to f of qt, then the thing you have to do over and over again is evaluate f at various intermediate stages that look like q plus an increment, q at the old time plus an increment. And you do that four times, and then take a weighted sum, and that gives you the analog of Simpson's rule for approximating the integral tn plus delta t of f of q of t. And it's fourth order accurate. So again, what is our, for this problem here, we do something slightly more elaborate because we compute our Runge-Kutta method to evolve the solution in time, and then at the very end, we say un plus 1 is equal to what comes out of the Runge-Kutta method times pH. So it's a slight variation on doing Runge-Kutta, and the reason you have to do this is because what comes out at the end of Runge-Kutta may not be exactly divergence-free. So here's the FFT solver for Poisson. We discretize on a power of 2 grid. We compute normalized complex forward FFT, compute the Fourier coefficients obtained by multiplying f by the symbol, and then compute the inverse FFT. Again, what I'm giving you this, and it's not simply I'm talking about it, you also have these slides, or we'll have them shortly, is that this gives you some idea of the level of detail I'm looking for. I would like to be able to read your proposal as someone who knows something about your application and knows something about the kind of both the mathematics and the science, and be able to say, this looks reasonable. So that's the level of the level of detail that I would like to see for that second milestone, the discretization milestone, is to be able to say at a mathematical level, this is what we are going to do. How about the third piece, the software design? So there are a bunch of general statements. One is that you want to use the mathematical structure of your algorithm as a basis for your software design. We've seen what the mathematical structure of this algorithm is that, in fact, it's almost inherited from the mathematical structure of the original problem. It's computing various operators, advection, projection, Poisson, things like that, and then combining them together in something that manages Runge-Kutta time evolution. At the bottom, you have to have classes for, you have to have classes for data containers. A lot of what you're going to be doing is acting on data. And so you have to have classes that define data containers and low-level operations on them. And then you have to have classes or functions for operators. So how do I compute advection? How do I compute how do I compute a projection? Depending on whether it's a class for a function or a class for an operator depends on whether the operator has state or needs to be used as a template parameter. So that second one is kind of an obscure thing, and I'll show you what I mean right now. So here is the way that you will be using this class in homework assignment 4, because this is what we'll be using to do particles. So this is a a way of implementing RK4, fourth order Runge-Kutta, and it's templated class. It's templated on the value of the state of what you're evolving in time, the value of a class that defines how you compute the right-hand side, and a class that contains kind of a reduced form of the state. It's the increment in the solution. So let me go back to Runge-Kutta and point out to you where these things are appearing. State is Qn. Notice that so state is Qn. The increments are these Ks. These are things we increment the solution, and actually it's Ks times weights. And then the function f combines doing incrementing Qn and applying the right-hand side. So that's how Runge-Kutta abstracts, how RK4 class abstracts this. And it abstracts, so it has increment, right-hand side, state, right-hand side, increment, and it has one function, which we write. It's a function advance that takes you from time step n to time step n plus 1 using Runge-Kutta. And then you have these data members. This has an internal data member, which is an increment, another internal data member, which is delta, and then an internal data member, which is how you apply the right-hand side. So in advance, this guy here, this is a class, but it could have just as easily been, it's really a function, it's really just a function. The only member of this class is a function member, which is an operator parens that is called to compute the increments in the solution in RK4. And it has this set of arguments. From the point of view of the templated class, this is what function has to look like. This is your contract that you're programming to, is that your class f will have a function that takes dx and x and two doubles in this fashion that has the effect of incrementing and applying the right-hand side. So this is an example of an interface class done purely with templates. We could have done this with inheritance, but in fact we can do it with templates because the thing that we might have used to derive, which may have been f, it could have been all of these things could have been defined in the derived class. We don't have to define them, and in fact we don't want to define them in the derived class. We can do everything with templates, and therefore we do. X comes in as an argument to advance, so it's coming in from the outside. So one of the things about this is that X, as an operational matter, keeps track of any time-dependent context required to execute the other operators. dx looks like K and is very lightweight. It's a data holder for the information required to increment the solution. And as I said, f is a class, but it's really just a function pointer. So again, this is the kind of information that you will need to provide me in, or provide us in the third milestone. Here's another, and let me just keep going through it. Now that you've seen what fourth order Runge-Kutta is, now I have to tell you the pieces that plug into this. We have a compute Euler right-hand side class that implements this projection applied to the divergence, applied to the advective derivatives of u, and conforms to the f template parameter interface that I gave for Runge-Kutta. Here's what the operator class looks like, or at least the header for it does. We have an operator that's just parens and takes these 5 arguments. So that conforms to the contract for computing a right-hand side in fourth order Runge-Kutta. Here's an example for, here's what field data x, what the x class looks like, the state class looks like for incompressible flow. You have to have certain member data. Some of the member data is things that are not required for the programming by contract. It's fill ghosts. You have to have increment. Imposed constraint is that final projection I was talking about. And then you have member data. Components, mgrid, and then the dimensions of the grid. And of course, a rectMD array. Here's the DX class, and again, what I'm specifying here is what the header looks like. So the pattern you want to see emerge here is for the third deadline, you need to have enough of an idea of what you're doing so that you can specify headers and you can specify what they correspond to in your algorithm description. Here's another one. This is not part of the Brungakutta class, but it's an important component of what you do. It's the thing that computes the approximate projection and manages that. So you can apply projection, it computes a gradient, computes a divergence. And then for that needs a Poisson solver, an FFT Poisson solver. Here it is. Finally, I think this is the last one. This is your advection operator, and so it provides as output div UU. It takes as input field data and a box and a mesh spacing. So this last set of header files and connections of the header files to the mathematical description of the algorithm is what I would want to see by the end of November. So questions on this? Yeah.
If we want to have some sort of graphical output, do we need to write our own visit writers?
Talk to me about that. There's a lot of visit resources we have around. So things like that. There are resources that we have laying around that you should consult with. I mean, this is not something you do in a vacuum. We have expertise. We have resources. You should talk to us. Well, I don't have to encourage you to do that. I got more information from the visit team on your problem, so we should talk about that too. Other questions? Yes.
Along those lines, is all of the code going to be written by us, or can we use packages that already exist?
That's part of your. I think that needs to be part of your. I'd like to see that as part of your spec. So I think, for example, here are the things you should obviously use. You should never write your own linear solvers for dense linear algebras. You should never write your own FFT. I mean, that's the whole point of homework 3, is to demonstrate why you should do that. When we start talking about kind of higher level components, there are performance issues, there are trade-offs. That's, again, a discussion point, and maybe I should put that into one of the things you talk about in probably stage 2. When you talk about discretization methods in the second milestone, talk about what the major components are, either in milestone 2 or in milestone 3. It's a negotiable point, but we do need to talk about it. Other questions? Okay, so I have just couple more slides here. One of them is about how to organize your project. So we've been sneaking up on this in this course, is that and what I've been sneaking up on is adding more capabilities to the way you think about makefiles with each assignment. So in the one that you just received for FFTs, we have the major new things that we have in there are how to make libraries, build libraries, and how to have make, call, make as part of the build process. So in assignment 4, I will finish this job, and you will have kind of a full model, if you like, of how we want you to organize your projects with respect to what your directory structure looks like and what your build system looks like. So you will have a main directory, which is my project, whatever it is, whatever the name you give it is. And then here are the main subdirectory, code and documents. And then under code, here are the kinds of things that we have. Source, you've already seen that, or multiple source directories, or subdirectories of source. So we've done the first pattern and the third pattern. And those contain your .h and .cpp files. They contain your unit tests. And here's something we haven't done yet, is that we haven't kind of separately created and used the possibility of having a separate parking space for .o files and .d files. And in particular for .d files, it's a very useful thing to have. So you'll see that in homework 4. We'll show you how to do that in Make. Another directory that you've already seen is having the place where your main program lives and that you execute out of, the exec directory, or you can have multiple exec directories. You can have a live directory. You're seeing that in homework 3. So that's where you put .a files. And then finally, here's something we haven't done yet, we'll do in homework 4, is having a separate place and one place for your application to look for all the include files it needs. So essentially what you do here is what we've already done with the live files in homework 3, is that as you build your capabilities, you copy the include files, you don't copy and delete, just copy them into one include directory for that problem. And that means that when it's time to do your include, you just include everything, you just give the -i home/include, and it knows where to find all the include files. So there are multiple reasons for this organization. You've seen some of them. It's to some extent it's accommodating GMake, but and it's also allowing you to it's trying to keep everything organized so that your eyes don't glaze over where you see a lot of extraneous stuff when you look at a directory. It's remarkable the extent to which that can be a distraction and can cause you to miss things that you shouldn't miss. Now in your documents directory, you're going to have 3 documents. A design document, which is essentially the documentation that you're producing in these intermediate stages. A Doxygen document, which is your Doxygen header files for the project, and then a final report. So everything should be buildable by invoking make all inside of code/exec. It's not that all the build is going to be contained in that one make file, but it will give you the ability to invoke make files that are in other directories. So again, you're seeing an example of this in homework assignment 3. So this is the organizational structure we want to see all projects conform to. So finally, what are unit tests? So for each class, you want to test member functions to see whether whether they have been correctly implemented. So you can't, as a practical matter, you probably can't develop comprehensive testing, but you want to actually have you want to at least have a place to park these tests as you identify problems and develop them as part of your debugging process. So here's an example of the kinds of things you would want to do. This is a typo here. That shouldn't be divergence of vec u. That second curly. So yes, that is actually correct. So divergence of a vector field that's identically equal to a constant. That isn't a typo. That's correct. Should be equal to 0. That's something for any differential operator. That's something you should check because if it's not true, then you have a bug or an indexing error. Another thing that you should check, and you've already seen this in homework 1, where you had a discretization of Poisson's equation of the Laplacian, and what you were testing for is whether that had a truncation error of order h squared, the advertised truncation error. That is a remark for those of you who are doing kind of discretization things, whether it's ODEs or PDEs. Checking convergence is a remarkably sensitive test for whether you have bugs, because particularly as you go to higher order, where it's non-trivial to to get fourth order without having made and still have a mistake somewhere, that tends to be quite subtle. So the obvious mistakes are often gotten from convergence tests. A more general statement of this first one is known analytic behavior for small systems. So when you get the particle assignment, in homework 4, the first 2 parts of the particle assignment are do 1 particle and do 2 particles. So if you do 1 particle, it shouldn't move. And in fact, that's a property of the discretized system as well as the differential equations. If you do 2 particles with a attractive logarithmic potential in 2 dimensions, if you set up the signs correctly, they should just circle around each other. So this is for vorticity, where you have where you can do that. So the forces can be attractive. Again, those are good debugging tools. They catch a lot of bugs. So forgetting to multiply by delta t is a common bug you find in doing Runge-Kutta methods. And boy, does this, the 2-particle test really catch that, because you very quickly kind of go out in the weeds. Unit tests should have their own make files and make targets. Unit tests grow in time. As you identify and fix bugs, you want to be sure that they stay fixed. So you want to have a unit test that exercises the fix of the bug, and then every so often you want to run the unit tests to make sure that the bugs stay fixed. That again is something that I'm hoping I will see in your development process for the final project. So any other questions? Does anyone see anything I'm missing here? Yes?
I guess, so what do you want in the final report for the project? Do you want like a summarize of, like us to summarize through kind of procedural steps?
I think that you want to have, the final report will be, some of it will be a concatenation of the first 3 milestone reports. But some of it is going to be it's going to have more context, because part of the final report is what is the problem that we're going to solve for this. Now you have solved it. So it's a discussion of what do solutions look like, how do I know I've gotten the right answer. So that one is more vague than the others. It's because that starts impinging on what kind of science problem you're interested or worrying about. Other questions? Okay, so I think we're done for today.